Hello everyone, my name is Nikita Black and I'm happy to see you on my channel. In the last video, we managed to clear and present an image with Vulkan. We did this by clearing a swapchain image directly. It was a bit boring, so we decided to do the same thing, but this time using a render target. Yeah, I can already see the excitement in your eyes. The idea is simple. Render to an off-screen texture and then somehow present the texture on the screen. Spoiler alert, we cannot present random images directly. Only swapchain images can be presented. So we need to find a way to move the data from our render target to a swapchain image. In this video, we will learn how to create an image. As it turns out, this is a surprisingly long process. It involves GPU memory allocation, which is quite complicated and consists of many steps. Thankfully, there are tools that make our lives much easier. We will also write a couple of shaders along the way. So grab yourself a coffee, just like I did. I think you're going to enjoy today's video. That's the current state of our application. We have a window that we can resize. We can rebuild the swapchain and we can clear the color. But last time we discussed that this implementation is not optimal. One issue is that when we close the application, we get a lot of warnings. And another issue relates to performance. Let's look at the diagram and try to remember what's happening. As a reminder, this is a timeline, CPU timeline and GPU timeline. Because the CPU and GPU are two separate devices, or you can think about them as two separate processes, they are completely independent of each other. The problem was that for frame 0, for example, we are using some resources. In our case, these resources are semaphores and command buffers. After we finish the frame, since these resources are used by the GPU, by another thread, by the driver, by another process, we can't start the next frame immediately, so we have to wait. If you look at this picture, we can see that while the CPU is preparing the next frame, the GPU is idle, basically it does nothing. It waits for commands from the CPU, and vice versa. Then the GPU starts its work, the CPU does nothing. It waits until the GPU completely finishes the frame. And we have this bubble on both CPU and GPU timelines. The solution to this is actually pretty straightforward. First, let me update this diagram with the resources we have. I just added this block indicating that this frame uses resources set number 1 in this case. The solution is to have multiple sets of these resources. That means that after we finish this frame, we can start the next frame immediately. If we have another set of resources available, of course. For example, like this. Here I completely removed this wait block. As we can see, we finished the frame and can immediately start the next frame on the CPU, while the GPU in parallel does its work for the previous frame. We can use another set of resources to start rendering the next frame, frame 2 in this case. For this setup, we require 3 different sets of resources. And this can continue indefinitely. As you can see, there is a problem. We need to create multiple copies of these objects and store them. For semaphores and maybe command buffers, this is not a problem because they are lightweight, but in the future, we will see that we need to do this for different kinds of buffers and images, and this can be quite costly. Imagine you have 4K resolution and want to render to a rendered target. You need a 4K render target for this. If you want multiple sets of these resources for different frames, you need to duplicate them. Basically, you will use a lot of GPU memory for each of these 4K images. And you can have multiple images of this kind, along with additional buffers. So we can't keep many sets of these resources alive. We need to limit ourselves to some reasonable number. In our case, this number will be 2. And this number has a name: frames in flight. The term frames in flight is quite common in graphics programming. So we will not use 3, I will delete this. Now if you look at this image closely, you can see another problem. Here, frame 1 finishes slightly faster than frame 0 on the GPU. That means if you want to start the next frame and reuse these resources, we need to be sure that they are no longer being used. But this is not the case in this diagram. This means that we still need some sort of barrier. We will use a special Vulkan object called a fence. If you remember, we already discussed what this means. Basically, a fence allows the CPU to wait until the GPU is ready. For each resource set, for each frame, we will have a separate fence. And this is how it works. When we submit work with the submit command, we also specify the fence associated with this frame. We will have one fence for each frame in flight. Then, before we start the frame, we need to check whether the corresponding work for that resource set has finished or not. If the GPU is ready, we can proceed immediately. So, for example, if our GPU is very fast, we will not wait at all. But if the GPU is much slower than the CPU, we will have to wait. We have to do this in any case to avoid overlapping frames that reuse the same resources. As a summary, we need to maintain multiple resources per frame in flight. In our case, the number of frames in flight will be 2. We will have semaphores, command pools, and a new object, fences. And we will cycle through these resources every frame. Let's write some code. It should make everything a bit clearer. Excellent. Let's go step by step through the changes. First, I replaced the image available semaphores and command pools with vectors. The rendering finished semaphore is a special case, and I left a link with a detailed explanation. But briefly, image available semaphores form a strong dependency. We never start rendering to an image until it is ready to use. And we can guarantee this because we control both the wait and signal operations on that semaphore. Rendering finished semaphores, on the other hand, do not provide the same guarantee because Vulkan does not give us a way to specify a signal operation for presentation completion. In other words, we never receive a signal indicating that image presentation has finished. Fortunately, this is easy to solve by making the number of rendering finished semaphores equal to the number of swapchain images rather than the number of frames in flight. Refer to the article for a more detailed explanation. Previously, I used the same number of both semaphore types and never had any issues. Probably that was luck. Recently, a validation check was added and the validation layers now report an error, then this rule is violated. We can now create these objects during initialization. As you can see, semaphores and command pools now stored in vectors. Next, in the start frame function, the first thing we need to do before every frame is to verify that the corresponding resources are free to use. As shown in our diagram, we check the fence before starting the frame. I also introduced two new variables: frames on flight, which is a constant, and frame index, which is updated cyclically every frame. In our case, the frame index alternates between 0 and 1, and I perform update at the end of each frame. The first frame uses index 0, the second uses index 1, the third uses 0 again, and so on. We use this frame index to access the corresponding resources. To guarantee that these resources are not still in use, we wait for associated fence. The fence is created in the createFence function. It is very simple. The only interesting part is the usage of fence create signal bit, which means that the fence starts in the signal state. This ensures that the first time we wait for it, the wait completes immediately. And this helps to avoid the need for special flags such as "Is this the first time a resource is accessed?" By calling wait for fences, we block execution until the corresponding frame has finished. Be careful here. This is not the previous frame. It is the frame with the same index, in our case 0 or 1. On the very first frame, the fence is already signaled as we saw, so the wait is effectively an all. Next, we reset the fence, because it must be in the unsignaled state when we submit work later. We do this with reset fences. Notice that the function name is plural, even though we reset only a single fence. After that, we perform the usual work and eventually reach the submission step. Here, we take the fence corresponding to the current frame index and pass it to the submit function. Let's look at what the documentation says. The fence parameter is optional. It is indeed optional because our application works without it. So basically, it's an optional handle to a fence that will be signaled when all submitted command buffers have completed execution. This means the fence is signaled once the command buffer has completely finished executing on the GPU, allowing us to check its state from the CPU. We use the same frame index in both start frame and end frame. Apart from that, everything works as before. The interesting part is the command buffer. As you remember, we allocate the command buffer every frame, and in our application we use only a single command buffer because the application is simple. The word allocate means that the memory is taken from somewhere. After finishing a frame, we cannot simply allocate another command buffer indefinitely. Sooner or later, we would run out of memory. On mobile devices, that would happen even sooner, because memory is much more limited there. To solve this problem, we use a separate command pool for each frame in flight. We take the command pool associated with the current frame and reset it. Resetting a command pool effectively returns all command buffer memory back to the pool so it can be reused. We could reset command buffers individually, but there is no reason to do so here because resetting the entire pool is simpler. In our application, the difference is negligible because we use only one command buffer per frame. However, in more complex application with hundreds of command buffers, the distinction can matter. After that, everything remains essentially the same. Let's see what happens when we compile. The project compiled successfully. Now let's run the application. It also runs fine. Visually, everything looks the same as before. However, the application now behaves much better because we no longer have unnecessary bubbles in the CPU-GPU pipeline. If you could balance CPU and GPU workloads so that each takes approximately 1 frame's worth of time, for example, about 60 milliseconds at 60 FPS, we achieve near perfect utilization for both processors. This is basically the goal of every real-time application. Keep both the CPU and GPU busy as much as possible. Now, when we close the application, we see warnings about undestroyed objects. Let's fix those quickly and then we continue. In the destroy device function, I call the corresponding destroy function for each object. Now we can compile and hopefully it will run and we will not get these errors anymore. We can do it one more time, we can resize, no warnings, excellent. Let's talk about what we can do next. As I mentioned several times, I want this application to support rendering to a render target. This means we first render to an off-screen image, and then we copy that image to a swapchain image. Strictly speaking, this is not necessary, because we could render directly into the swapchain image. However, I still want to implement it for several reasons. The first reason is that it is just interesting and gives us an opportunity to explore more aspects of Vulkan. The second reason is that it prepares us for future steps. Although rendering to a render target sounds simple, you render to one image and then copy it to another, it actually requires a number of more advanced concepts. One of those concepts is shaders. We need to create vertex and fragment shaders, because at some point we will want to copy the render target to the swapchain image using a full-screen triangle. This requires a custom graphics pipeline with custom shaders. In this video, we will see exactly what this means. We will also learn how to write shaders, how to compile them and use them in our application. Another important topic is memory management. We need to allocate memory for images, and this process is significantly more complex than memory allocation on the CPU. On the CPU, you allocate memory with a new operator and you free it with delete. On the GPU, the process is conceptually similar, but much more complicated because of the different types of memory available. A GPU can expose multiple memory heaps, and we need to choose the correct one depending on how the resource will be used. There are different types of memory: device local memory, host visible memory, host coherent memory, and others. Selecting the wrong type can lead to poor performance or even prevent the application from working correctly. Another challenge is that allocations must satisfy strict size and alignment requirements. Every padding and alignment rule must be respected. A small mistake may result in an exception in the best case, or a black screen in the worst case. On top of that, because the CPU and GPU operate asynchronously, we also need to think about synchronization. To make things easier, I will use a third-party memory allocation library. It is called Vulkan Memory Allocator, and it is developed and maintained by an engineer from AMD. In practice, it has become the de facto standard for memory management in Vulkan applications. Even though we will use the library, I will still show what happens under the hood. We will look at how memory types are selected and how allocations are performing. We will go through the process step by step in the debugger. So the first step is to add the library to our project. We will do the same way we added other third-party libraries before. Let's get started. Everything is very straightforward here. As before, I added a dedicated CMake list file for the library. I'm using version 3.3.0, which is the latest version at the time of recording. Then I simply make the library available using CMake fetch content make available function. We can look inside the library's CMake list file to find the target name. We then use that name to link the library to our graphics library target. What's interesting is that if you look at the source code, the library consists of only a header file. However, that header also contains the implementation. To make the implementation available, we need to define a special macro before including the header. We'll see how to do that in a moment. Now that the library is part of our project, we can start implementing our render target. In addition to the Vulkan Image and Image View objects, we also need to keep track of the memory allocation now. To keep everything in one place, I will create a simple wrapper class. Let's write some code. We define our wrapper similarly to how we did with Graphics Manager. Here I have a default constructor. As you remember, I don't want my functions to throw exceptions. And since the initialization of image can fail, and since a constructor cannot return a value, I moved all the initialization code into a dedicated init function. Let's look at the function declaration. We need the allocator, the device, the image format, the image usage flags, and the aspect flags. If you open the usage flag enumeration, we can see many different options, but in our application we will use only color or depth stencil. The same applies to the aspect flags. In our application, they will be either color or depth. Although Vulkan supports other aspects as well, in case we need something more unusual. And of course, we need the image dimensions. By the way, we will use only 2D images. That's why this wrapper is called Image 2D. The first thing I do here is calculate the image size in bytes. This is not strictly necessary, and I don't think we will actually use this in our application. However, I use it in some of my other projects, so I decided to keep it here as well. Let's look at how it's implemented, because it's quite interesting. In Vulkan, describing image dimensions only in texels is not always sufficient, because some formats operate on blocks. Vulkan supports several compressed formats, and these formats use different compression blocks extents. To calculate the block extent, we use the Vulkan utility function. Let's see how it's implemented. The function iterates over the supported formats and retrieves a format description. If you look at the format information, we can see fields such as block size, texels per block, and block extent. All supported formats are listed here. For a simple 32-bit format, the block extent is 1 by 1 by 1. However, if you look at a compressed format, such as BC2 for example, we can see that its block extent is different. In most cases, the block extent will be equal to 1, and in our simple application it will always be 1. Still, I keep this implementation generic. Once we know the block extent, we can calculate the actual block size in bytes using another helper function, texel block size. If you look at its implementation, we can see that an 8-bit format occupies 1 byte, a 16-bit format occupies 2 bytes, and so on. Finally, to calculate the total image size, we multiply the block dimensions by the block size. Next, I store some information inside the class. For example, the device and allocator are needed later when we destroy the object. After that, we fill out the image creation structure. We do not use any special image creation flags. The image type is 2D. The format and image dimensions are provided through the function parameters. We will not use MIP mapping in this application, so the MIP level count is set to 1. The same applies to array layers. We also do not use multi-sampling, so the image always has 1 sample per pixel. The tiling property controls how image data is laid out in memory. When we specify tiling as optimal, the GPU is free to arrange the image data in whatever way it considers optimal. The exact layout may differ between GPUs. For the best performance, it is generally recommended to use optimal tiling whenever possible. The downside is that image data stored in an optimal layout is not directly readable by the CPU. If you try to access it, we will see GPU-specific encoded data, and the exact memory representation is usually not documented. If you need to read image data written by the GPU, we can use linear flag instead. In that case, the data is stored linearly in memory, making it possible for the CPU to read and interpret it. Next come the usage flags, which we receive through the function parameters. The following 3 fields are related to queue ownership. As you remember, Vulkan applications can use multiple queues. If an image needs to be shared between queues, we must specify that here. We will only use a single queue, so the sharing mode is set to exclusive. Because of that, the remaining queue-related fields can stay at their default values. The initial image layout is set to undefined. This simply means that when the image is created, we make no assumptions about its contents. We don't care what is stored there, because the image will be overwritten before it is ever used. Next come the Vulkan Memory Allocator objects. Here we create the image using createImage function. I promised to put a breakpoint here and show what happens internally, so let's do that now. Later we will step through the implementation and see how it works. We use the dedicated memory flag. The documentation for this library is excellent, and most of the information can be found directly in the header files. The library also provides many examples covering common usage patterns. This flag requests a dedicated allocation for the image. Next, we set the usage to auto, allowing the library to determine the optimal memory type automatically. We do not specify any required or preferred memory flags, and everything else is left as its default values, because these two fields are all we need. Then we call the function and hope everything works. Once the image has been created, we need to create an image view. I decided to keep both the image and its view inside the same class. To create a view, we first define the subresource range. We already saw this process when we created image views for the swapchain. As mentioned earlier, we do not use MIP maps or multiple array layers. Next, we fill out the image view creation structure. Technically, the image and the view can use different formats, but that is not the case here. We can also remap image components when they're accessing the image through the view. For example, we could map the A component to B or G. We won't be doing any component remapping in this application. Finally, we call createImageView. At this point, the image is ready to use. I also have a destroy function that releases everything we created. It first checks whether init was actually called. If not, the function simply returns without doing anything. After destroying the resources, the object is reset to its initial state. Finally, I added a few getter functions that we will need later. Now that we have our image2D class, we need to create the allocator itself. As you remember, the allocator is responsible for managing GPU memory. We will create and initialize it during the initialization step. The first thing we need to do, even before using the library, is mark it as a system library. In this case, CMake treats the library's directory as external code rather than our own code. This is necessary to avoid compilation errors. If you remember, in our application we treat every warning as an error, and this library produces a few warnings. For example, there are warnings about unused variables. These are not critical, the code is still correct, but since the library is header only and we include it directly in our code, all of its warnings become our warnings. With the warnings as errors flag enabled, those warnings turn into build errors. This is what I mean. If I remove this setting and try to compile the project, we immediately run into problems. For example, warnings about old style casts or unused parameters. By marking the directory as system, we tell the compiler to ignore warnings originating from that library. The next thing is how definitions are provided by this library. The library is header only, but not all functions are declared as inline. Some functions' definitions are hidden behind a macro. To avoid linker errors, we must enable those definitions in exactly one source file. In our case, we will do it in Graphics Manager CPP. Let's see what I mean. If we comment out this macro definition and try to build a project, we get a large number of undefined reference errors. The linker simply cannot find any implementation of those functions. On the other hand, if we define the macro in multiple CPP files, we violate C++'s one definition rule, which requires that a non-inline definition exists exactly once in the program. Let's rebuild the project and remove all the errors. Now let's see how we create the allocator. The library follows the standard Vulkan pattern. First, we create and fill out a create infrastructure, and then we pass it to a creation function. Here we use only the required fields: the physical device, logical device, and Vulkan instance. There is also a flags field. To be honest, I don't remember whether we will need it in this project. I included it because in another project I use some newer Vulkan enumerations that require additional allocator flags. I'm not sure whether we will encounter the same situation here. For now, let's simply set it to 0. If we run into any issues later, we can always bring the flag back. The interesting part is what happens internally when the allocator is created. As soon as we create the allocator, it allocates several large blocks of GPU memory. The size of each block can be controlled through this parameter. In our case, a value of 0 means the allocator uses its default block size of 256 megabytes. The number of blocks depends on the number of available memory types. We will see shortly what that means. Of course, if a block runs out of space and additional memory is needed, the allocator can create new blocks as long as the GPU has enough memory available. With the create infrastructure filled out, we can finally call the allocator creation function. Let's put a breakpoint here and see what actually happens under the hood. I call the create allocator function immediately after I create the device. Now I press F5 and wait until we hit the breakpoint. Let's go inside the function. Here the library performs some checks, and we skip everything until the call to this vmanew function. This call eventually invokes the allocator constructor. I also skip checks that are not interesting for us. Here it sets some variables to 0. Next, it imports Vulkan functions. This is interesting. When we built our project, we link against the Vulkan library that CMake found. Basically, we are linking against the Vulkan loader, which is normally installed with the graphics driver. The loader exports Vulkan entry points and, at runtime, dispatches calls to the correct driver implementation based on the Vulkan object being used. There can be multiple implementations. As we saw earlier, On my machine, I have two different devices and a software implementation. So during the call, the correct one must be selected depending on the device we chose. This runtime dispatch has some cost, and there are different ways to obtain a function address, either by loading it manually or by using a library like Vulkan. This is an advanced topic, and we are not using it here. We rely solely on the loader. Here the library calls getPhysicalDeviceProperties, the same way we do in our code. Next, it retrieves device memory properties. We can see that we have 2 heaps and 6 memory types. Next, again we skip some checks. Then it calculates the block size for allocations, since we passed 0 as a parameter, as mentioned earlier. We can see that it uses 256 megabytes per block. Next, the function performs some memory type checks. For some reason, it skips a memory type with this flag enabled. Since I'm using NVIDIA, this is not relevant in my case. It is interesting how memory types are represented in Vulkan. Since GPUs usually expose more than one memory type, all types are encoded into a single uint32 value. For example, if you have 3 different memory types, the memory type bits would be equal to 7, which is in binary 111. Later, when we allocate an object, we first check its memory requirements. In these requirements, there is also a uint32 value with memory type indices encoded. We then compare these required flags against the available memory flags. We will see this in action later. Here we can see how the library creates blocks for each memory type and sets up alignment, granularity, and other important parameters. At this point, it doesn't allocate any actual GPU memory. It only creates empty blocks for future use. We will see the real allocation when we create an image. So this library does all the heavy lifting for us. That's basically it. The init function itself doesn't do anything interesting in my case. It just skips the body entirely. All we need to remember for now is that the allocator performs some checks and stores information for future use. Now that we have the allocator, we can start creating images and other resources. But there is an important question: how many render targets do we actually need? If you remember, we currently maintain multiple resources per frame in flight. Should we treat the render target as another per frame resource? The answer is no. Let's look at the diagram again. As we can see, frames execute one after another on the GPU. There is no overlap between complete frames. Technically, the GPU can overlap certain types of work. For example, it might process vertex work for one frame while still performing fragment work for another. However, we synchronize access to frame resources using barriers. Because of this, a single render target is sufficient. The key point is that the render target exists entirely on the GPU. We never access its memory from the CPU. Since all access is synchronized through barriers, we can safely reuse the same render target every frame. In other words, one render target is enough because we guarantee that it will be accessed serially. Now let's create our first image. I added 2 new variables to the graphics manager: the render target image itself and its format. We will need the format in multiple places, which is why I store it in a separate variable. We set the render target format once during initialization. Here I use a hard-coded value. This may seem unusual, because in Vulkan you generally cannot just pick something and assume it will work. As you know, we usually have to enumerate capabilities, request features, and verify that they are supported. However, there are exceptions to this rule. Certain features and formats are guaranteed by Vulkan specification, and this format is one of them. We can verify this by looking at the specification. There is a section called Required Format Support. Here we can see a table with different requirements. This checkmark indicates that the feature must be supported. We need to scroll down and find our format, which is a 4-byte format. As you may remember, when we created the swapchain, we specifically requested an sRGB format. I want to use an sRGB format here as well. As a reminder, with an sRGB format, conversions between linear and non-linear color spaces are handled automatically by the hardware. We will use this image for sampling, and as we can see, sampling support is guaranteed. We will also use it as a color attachment, and support for that is guaranteed as well. Next, we create a render target. We do this inside the resize function because the render target must be recreated every time the window size changes. We always want the render target dimensions to match the size of the window. We provide the allocator, device, and format. Then they specify the usage flags. I already mentioned these usage flags when discussed the format. We will use the image for two purposes. First, we will render into it. Second, we will read from it when copying its contents to a swapchain image. Reading from an image in a shader is called sampling. Since this image stores color data, we use the color aspect flag. Finally, we provide the image dimensions. Of course, we also remember to destroy the image in the cleanup function. This returns the memory back to Vulkan Memory Allocator's internal pool. That's basically it. Every time the window is resized, we recreate render target. Now let's see what the library actually does under the hood when we allocate GPU memory. I start the project under the debugger. First, we enter our init function. Just out of curiosity, we can verify that the block extent is indeed 1 by 1 by 1, and the block size is 4 bytes. This is exactly what we expect because we are using a simple 4-byte format. Now we can also see the total image size in bytes. Next, I skip ahead to call to the VMA function. Let's go inside. Here I skip several validation checks, and the first interesting thing we see is that the library creates a Vulkan image object. At this point, it is just a Vulkan object. No memory has been allocated yet. It is simply a handle that we can use when we want to perform operation of the image. Next, the library requires the memory requirements for the image. Here we can see that Vulkan returns memory type bits. In our case, the value is 3. If you look at 3 in binary form, it is 1, 1. This means that out of 6 memory types available on this GPU, only memory types 0 and 1 can be used for this image. Next, the library calls its allocation function. Let's see what happens there. Again, I skip a lot of checks, and here the library tries to find a suitable memory type. We already know that only memory types 0 and 1 are candidates. The library now evaluates both options and selects the better one. Here we can see that the memory type of index 1 is selected. Here we can see that the allocation will come from heap 0. Finally, we arrive at the Vulkan call pk allocate memory. This is the call that actually allocates GPU memory. In our case, the allocation succeeds. For memory types that are visible to both the CPU and GPU, Vulkan allows us to map that memory into the CPU address space. If necessary, the library performs that mapping automatically. In our case, however, we are creating a device local image. Because of that, the memory is not mapped. Later, when we create resources that must be accessed from the CPU, we will see how memory mapping works. Eventually, the allocate memory function returns success. At this point, we have two separate things: a Vulkan Image object and a block of GPU memory. These two objects exist independently. They do not know about each other yet. However, whenever we use a Vulkan image, Vulkan must know where that image resides in memory. To establish this relationship, we need to bind the image object to the allocated memory. This happens in the bind image memory function. Let's see what it does. The library simply calls Vulkan's vk-bind-image memory function. After this call, Vulkan knows that this image object is baked by a specific region of GPU memory. And that's it. You can see how many steps are involved in what appears to be a very simple task, creating an image. Now, let's see why the library chose one memory type over another. To inspect the memory types available on our GPU, we can use the Vulkan Info tool. We have already used this tool before. One interesting thing is that if I generate a JSON report, it doesn't include memory properties. However, if I generate an HTML report, it contains much more information. Here we can see that the tool generated the HTML file. Let me open it in the browser. We can see my 4 available devices. I am interested in device 0, which is the NVIDIA device. Let's find the memory properties section. Here it is. We can see that the device exposes 2 memory heaps and 6 memory types. The first memory heap is GPU memory. As we can see, it contains 16 GB of memory. The second memory heap is system memory. In my case, about 23 GB is available. This heap doesn't have any special flags. Now let's look at the memory types. Memory type 0 points to heap index 1. As we can see, and as we just discussed, heap 1 corresponds to system memory. However, we wanted to create a GPU image, so memory type 0 is not the ideal choice. Memory type 1 points to heap index 0, which is the dedicated GPU memory heap. This is the memory type that was selected for our image. We can also see that this memory type supports image allocation, including both color and depth images. All of these memory types are suitable for buffer allocations. Memory type 2 doesn't list any supported image usages at all. What's interesting is memory type 3. It supports color images, but only if those images use linear tiling. As you remember, our image uses optimal tiling, so this memory type is not suitable for our case. The same limitation applies to all other memory types as well. That's basically it. As you can see, this is a very useful tool for understanding the capabilities of a Vulkan device. So I recommend using it whenever you need to investigate hardware-specific behavior. Now that we have the render target, we need to replace clearing the swapchain image with clearing the render target. After that, we need to present the render target to the screen. In other words, we need to copy the render target to a swapchain image. Technically, we could do this by directly copying the data from one image to another. However, we will use a different approach. We will draw a full screen triangle and use the render target as a texture. This approach has several advantages. For example, the render target and the swapchain image can have different resolutions. I know that this is not the case in our application, because both the render target and the swapchain always match the window size. Still, it is a useful capability to have. Another advantage is that it allows us to add post-processing effects. For example, we could implement blur, bloom, tone mapping, or many other techniques. I drew a simple diagram to illustrate the idea. The dashed rectangle represents our window. We draw a single triangle that completely covers the visible area. At first glance, it may look like there are empty regions around the edges, but those regions are ignored by the hardware. In the end, only the portion that overlaps the viewport is rasterized and shaded. Of course, we could use 2 triangles instead, like in this image, or even more. However, a single triangle is simpler because it requires only 3 vertices and no stored geometry at all, as we will see shortly. There is another important detail, and it relates to how GPUs execute fragment shaders. When a GPU rasterizes a triangle and executes fragment shaders, the smallest execution unit is not a single fragment shader invocation, but a group of 4 pixels, commonly called a quad. Fragment shaders are executed in 2 by 2 groups. This behavior serves several purposes. For example, it is used when calculating derivatives and then selecting mip-map levels. Interesting things can happen along the triangle edges. Consider the edge where 2 triangles meet. Because fragment shaders execute in quads, some shader invocation near the edge may be performed twice. In other words, we can end up with redundant fragment shader executions along the shared boundary. This is not a problem for our application because our fragment shader is extremely simple. However, avoiding these redundant executions is easy, so we might as well use the modern approach. First, let me write the shaders. After that, we will have a longer discussion about how all this works. Let's start with the vertex shader. As you can see, it is very simple. There are many different ways to write shaders for Vulkan. GLSL, HLSL, Slang, or even Sphere directly. In this application, we will use GLSL. At the top, we specify the GLSL version. The shader must also output the position. This is required by the hardware so it can perform operations such as clipping, culling, and rasterization. In addition, we output UV coordinates for our texture, which in this case is the render target. These UV coordinates are passed directly to the fragment shader and automatically interpolated across the triangle. The interesting part is how we invoke the shader. When we issue the draw call, we tell the GPU to render 3 vertices. As I mentioned earlier, we do not store any geometry at all. Instead, the built-in variable, vertex index, is automatically set by the GPU. In our case, it will contain the values 0, 1, and 2 for the 3 vertices of the triangle. Using a simple formula, we calculate both the UV coordinates and the vertex position directly inside the shader. Let's look at the diagram. Here we will work with 2 different coordinate spaces. The first is UV space. In Vulkan, the UV origin is located in the top left corner. This corresponds to the coordinate 0, 0. As we can see, the right vertex of the triangle receives a U coordinate of 2, while the bottom vertex receives a V coordinate of 2. We can easily verify this by substituting the values 0, 1, and 2 into the UV calculation formula. The resulting UV coordinates match the ones shown in the diagram. To calculate the actual vertex position, we work in a different coordinate system called Normalized Devised Coordinates, or NDC. In Vulkan, the origin of NDC space is located at the center of the screen. The x-axis points to the right, the y-axis points downward, and the z-axis points into the screen. For a screen space triangle, we do not need the z-axis, so the coordinate will be 0. Looking at the diagram, we can see that the top left corner corresponds to the coordinate -1, -1. The right vertex of the triangle has coordinates 3, -1. And the bottom vertex has coordinates -1, 3. Again, we can verify this by plugging the UV coordinates into the position calculation formula and comparing the results with the diagram. This is how they generate a full-screen triangle entirely inside the vertex shader, without storing any vertex data on the CPU or in the vertex buffer. The fragment shader is a bit more complicated. As before, we start by specifying the GLSL version. We also need to enable a GLSL extension required for a feature we will use in this application, descriptor indexing. Next, we define some push constants. Push constants allow us to pass a small amount of data directly to the GPU through the command buffer without creating any buffers in memory. After that, we describe how the shader can access textures. In our case, the texture is the rendered target. Next comes the UV coordinate that the vertex shader passes to the fragment shader. Finally, the shader produces an output color, which will be written to the color attachment. In our case, the color attachment is a swapchain image. So the fragment shader reads data from the render target and writes it to the swapchain image. This line is the one that actually performs the read. We use the standard texture function to sample the render target. We will use a so-called combined image sampler, where a single descriptor contains both the image and the sampler state. That is why you do not see a separate sampler declaration in the shader. We will see how to set this up shortly. The most important part of this line is the non-uniform ext call. This is related to descriptor indexing, which in turn is related to how GPU hardware executes threads. It is important to remember that GPUs do not execute threads individually. Instead, they execute groups of threads together. In Vulkan, such a group is called a subgroup. The size of a subgroup depends on the hardware. On NVIDIA GPUs, it is always 32 threads. On AMD GPUs, it is usually 64. Intel hardware may support different sizes. A subgroup is effectively the smallest unit of parallel execution on the GPU. Normally, if you access a descriptor array using an index, the compiler assumes that the index is uniform across the entire subgroup. In other words, it assumes that all threads in the subgroup use the same value. However, this is not always true. Different threads may need to access different descriptors. In our case, the index remained the same for all threads, so we would not see any problems. But imagine a more complex shader, where the index is selected dynamically. In that case, different threads within the same subgroup could use different indices. Without non-uniform call, the compiler might optimize under the assumption that the value is uniform, resulting in incorrect behavior. The non-uniform call explicitly tells the compiler, do not assume that this value is uniform across the subgroup. Different threads may use different values. When working with descriptor indexing, you generally need to use this annotation whenever descriptor indices can vary per thread. At this point, you may wonder, why are we using an array at all? This relates to the architecture of the application and more specifically to descriptor indexing, also known as bindless rendering. I will cover this topic in detail in a future video. For now, here is the short version. In Vulkan, resources are accessed through descriptors. A descriptor is a small object that tells the GPU where a resource is located and how it should be accessed. For buffers, a descriptor mainly describes a memory address and size. For images, a descriptor contains additional information such as image views and sampling parameters. The exact representation of a descriptor is hardware dependent. From the Vulkan programmer's perspective, descriptors are opaque objects. We do not know how they are implemented internally, and Vulkan intentionally hides these details from us. Later, we will see why descriptor arrays are useful and what set number 1 actually means. For now, just focus on the purpose of the shader. This fragment shader reads data from the render target and outputs a color. The color is then written to whichever color attachment is currently bound to the graphics pipeline. There is one more important thing to understand. These shaders, these tiny programs, are ultimately the entire reason we are writing all this code. They are literally the programs we want the GPU to execute. It is funny when you think about it. Each shader is only a dozen lines of code, yet we write thousands of lines of Vulkan code to make them run correctly. Everything we have written so far, and everything we will write later, serve exactly one purpose: getting these small programs onto the GPU and executing them efficiently. Another interesting thing we need to figure out is how to bring shaders into our application. Looking a bit ahead, Vulkan requires shaders to be provided as compiled binaries in SPIR-V format. We need to create a shader module and then pass that module into a pipeline. There are multiple ways to handle shader compilation. One option is to take the shader source, exactly as written in GLSL, compile it at runtime, and then use the compiled output to create Vulkan objects. This would require compiling shaders every time we launch the program. We could also compile them once, store the result somewhere, and reuse it on the next launch. But at that point it raises the question: why not compile them before running the application in the first place? In any case, both of these approaches require storing shader files somewhere, and I would prefer to avoid dealing with the file system directly. So we will take a different approach. We will compile shaders before running the application and embed the resulting binary directly into the executable. The simplest way to do this would be to manually convert the binary into a uint8 array, place it in a CPP file and use it when needed. However, the problem is exactly that word: manually. Every time we change a shader, we would need to regenerate and update this file by hand. As all we know, programmers are lazy by design, so it is better to automate this process. For that, I will use a third-party library that helps with shader embedding. We will use CMake to build the shaders, and the library will handle embedding the compiled data into the application. At runtime, we will simply retrieve the binary blob. As usual, I first add the library to the project, then write the necessary CMake config to compile the shaders. After that, I will explain how the whole system works. I added a new library called CMake-RC. I'm using a specific commit here because the library is no longer maintained, and the latest tag doesn't work with the CMake version we're using. However, this particular commit works fine. For our purposes, everything we need from the library is contained in this file, which we simply include. After that, we can use the CMake functions provided by the library. Next, I define the helper function to build our shader files. First, we need the path to the Vulkan SDK. This SDK contains GLSlang validator, the tool required to compile GLSL shaders into SPIR-V binaries. If CMake successfully finds Vulkan, this variable will be populated, and we can use it to locate the tool. The names of GLSlang validator and other Vulkan-related variables can be found in the documentation for the CMake's Find Vulkan module, which has been part of CMake since version 3.7. Interestingly, the naming and the capitalization of these variables are not entirely consistent. But it's CMake, so that's fairly normal. Next, we define the CMake function itself. I know it looks a bit strange, and I have my own opinions about CMake, but since it has become the standard build system for C++, we have to accept some of its peculiarities. The first parameter specifies a prefix for all parsed arguments. For example, when we access target name, the variable will actually be called @compile_shaders command target name. We can choose any prefix we want. The next parameter lists options. These are Boolean-style arguments such as debug or green, single words that are either present or absent. We do not need any options in this function, so this field is empty. After that come the single-value arguments. Our function requires two of them: target name and output directory. Target name is the name of the CMake target that will contain our embedded shaders. We will see how to create this target shortly. Output directory specifies where the compiled SPIR-V files will be generated. The final group consists of multi-value arguments. Here we provide the list of shader files to compile. Next, we perform a few checks and iterate over all shaders. First, we verify that shader file exists. Then we create the output directory if it doesn't already exist. The next line extracts the file name, including the extension. These extensions are recognized by GLSlang validator. When we provide a file with .vert extension, the tool automatically knows it is a vertex shader. This is not strictly required. We could also specify the shader type through command line arguments. However, encoding the shader type in the extension is much simpler. Next, we call CMake's @custom command. This command tells CMake that it will generate a SPIR-V file at a specific location. The actual command invokes GLSlang validator with the required arguments. One of these flags tells the compiler to embed debug information into the generated SPIR-V. This is extremely useful when debugging shaders with tools such as RenderDoc. I always enable it, at least for debug builds. Next, we specify that we are targeting Vulkan 1.3. After that, we provide the input shader file and the output SPIR-V file name. We then specify that this command depends on the shader source file. As a result, if the shader changes, CMake will automatically rebuild it the next time we build the project. The final line is simply a comment that will be printed in the terminal during the build. The next statement uses a function from the CMake-RC library. Here, we add the generated SPIR-V file to the shader target. Again, we will see shortly how this target is created. Then, we define the prefix using the whence argument. This is important, because without it, we would later have to access the resource using its full path. That path depends on the machine where the project was built, so it would be different on my machine and on yours. Obviously, we cannot hardcode machine-specific paths into our C++ code. The whence argument removes the specified prefix from the resource name. As a result, we can access the resource using only its file name instead of the full path. To summarize, we use GLSlang validator to compile GLSL shaders into SPIR-V binaries. And we created this helper CMake function to invoke the tool automatically during the build process. Next, I need to add the CMake-RC library to our project. It is important that the include happens before we use any of the library's functions in CMake. This sounds obvious, but in practice it is not always straightforward. For example, in CMake, the order of target definitions doesn't matter. That is one of the reasons it can feel confusing at first. Here is how we create our shader target. We call CMRC add resource library, which creates a target named shaders. All dependency management is handled internally by this function. That is why when we build the project, the files are actually generated and embedded. Up to this point, our helper function only defined a rule for building SPIRV files. It doesn't execute anything by itself. By default, it is just a build rule. I know this sounds a bit strange, but that is CMake. Under the hood, the library creates a static library, which is then linked to our project. Inside that library, the compiled binary shader data is stored. Next, we call our helper function and provide the two shaders we currently have. We also need to link this library so we can access the embedded data. Now we can verify the setup. If I modify a shader file and try to build the project, it fails, then the code is incorrect. With valid code, everything compiles correctly, as shown in the build comment we added earlier. By the way, I forgot to add these braces earlier, so I fixed that now. Without them, the code would not compile. If you look into the build directory, we can find the generated SPIRV files. We can also see the static library that was created, and inside it, our shaders are stored as raw byte data. So again, we could do all of this manually, but instead, we only need to add a shader file to the helper function and everything is generated automatically. Awesome. We now know how to allocate GPU memory. We now know how to create Vulkan images. We even wrote a couple of shaders. But we still do not know how to retrieve shaders from their binary form in our SPP file. We also don't know how to bind this compiled shader data to a graphics pipeline. In fact, we do not know yet what a pipeline is. We also do not know how to tell shaders that they should read from the render target and write into a swapchain attachment. That is another thing we need to figure out. And honestly, that is a lot of work. For today, we are done. We already made good progress. Next time, we will finish the render target, learn about descriptor indexing, and start working with pipelines. That's it for today. Thanks for watching. Take care of yourself and your loved ones.